Okay, hello everyone. So this video is just to summarize what chapter 4 is all about. So we're going to focus on second order. It's linear with constant coefficient. So you'll have a y double prime with some sort of a constant coefficient in front. And then you have the term y prime with some sort of a constant coefficient in front. And then you have the y term with a constant coefficient, we'll call it c. And then the last term will be the term with no y, but it might involve the independent variable, and so we'll just put that on the other side. And I'll call it some capital F function of x, okay? So if it's a second order, it's linear, and you have constant coefficient with the y double prime, y prime, and y, then it looks something like this. This f here is not a constant. It could be an expression in terms of x. Okay? So an example of something like this might be maybe y double prime, so that means there's a 1 in front, minus y prime, okay, and then minus 6y is equal to, so I'm using x as my independent variable, so I'm gonna have to use x over here. You can use t as your independent variable if you want. So let's say I have x squared e to the 2x, okay? All right, so this here is my f of x. My capital A is a 1, my capital B is a -1, and my capital C is a -6. Okay, so our main focus is going to solve this type of differential equation. And so in chapter 4, the method on doing so is, it's very basic. It has to do with the type of function f, capital F is. But here we're going to break this down into two types of differential equation. The first type is non-homogeneous. So that means we're going to focus on the solution that would give us that capital F on the right side. Okay. And then we're going to consider the differential equation where it's homogeneous by making it 0 on the right side. So why would we want to consider something like this? Well, it turns out a solution to the homogeneous equation can be added on to this solution for this differential equation, and that would give us an additional solution to this differential equation. And you'll see in a bit what I mean. So let's say we have a particular solution, y of p is a solution. It's this guy, whatever y of p is, right? But the focus on this type of differential equation where we focus on this capital F is going to be in section, I believe, starting at 4.3, 4.4, and 4.5. The homogeneous case is covered in 4.2 and 4.3. Okay, so let's say y of p is a solution to this guy, which means that if I plug it in, I take y of p and I differentiate it twice. I take y of p, differentiate it once, plus c, and then here's this y of p. I will get this capital F of x. All right, so this is what you get if you plug in y of p. So y of p would satisfy that differential equation. Let's say over here you have a solution for this homogeneous case, and we'll call it yh is a solution. Okay, that means what? That means if I take a yh double prime plus b y sub h prime plus c y sub h, I will get 0, right? So if y of h is a solution to this homogeneous equation, differential equation, then when I plug it in, yh double prime plus b yh prime plus c yh, you will get a 0. And here we're going to claim that if yp is a solution to this guy, then I can take, let's say I'll call it we'll call it f. Just give it a different name, f of x here, where I'm going to take that particular solution and add it onto the homogeneous solution. Not only that, I can multiply by any constant in front. So we're going to put it in, let's say, a c, a lowercase c, not that capital C, okay? And we're going to claim that this is also a solution. And it's a solution to this non-homogeneous case. So how do I prove this claim, given that this is true and given that this is true? Well, if this is indeed a solution, then when I plug it into this differential equation, it should satisfy this differential equation. So let's try that out. So if I plug in f for that differential equation, that means that a, and I'm going to differentiate this twice for yp plus cyh, and that's yp plus cyh, but I'm going to differentiate once. Yp plus cyh, and this right now would be a question mark because we're trying to show that this is indeed going to give me that capital F of x. And so if this equation is true, then we've proven that yp plus any constant times the homogeneous solution is also a solution to this guy. Okay? Okay, so let's just kind of review back here. You start with a second order linear differential equation with a constant coefficient in front of the y double prime, y prime, and y. And we're going to solve this by breaking it up in two cases. The first case is the homogeneous case. The second case is the non-homogeneous. And let's say you have yp being a solution to this guy, yh being a solution to this guy. That means what? That means that when I plug yp into this differential equation, I should get my capital F of x. If yh is a solution to this differential equation, when I plug it in, I should get a 0. And then my claim now is that given that yp is a solution to this non-homogeneous case, it turns out you can take that guy plus any constant multiple of the yh, and it will still be a solution for this non-homogeneous case. The reason being really is that this yh term will end up just giving you a 0. So it won't really contribute to anything on the right side, whereas this yp will give you that f of x. And you'll see in a bit. Okay, if I take the second derivative, well, derivative is additive. That means that I can differentiate term by term. So this means that I'm going to take the second derivative of the yp. And if you differentiate a constant times a function, well, that constant is not affected. So it'll be c times yh double prime, right? Okay. If you differentiate yp plus cyh, it'll be yp prime plus cyh prime. And here you're not doing anything, so I'm going to leave that alone. And it's still a question mark because we're trying to show that it will give you that capital F of x. Multiply everything out, and you can separate things, but you'll get what? You'll get, and this is all just algebra, so I'm going to let you guys fill in that few extra steps in between. But you should get this. Oh, that's yp. Okay, and then you'll get the a times c, or c times a, right? It could be right in front. Y h double prime, b times cy prime. Well, I can put that c in front. And then c, capital C times lowercase c. I'm going to put that lowercase c in front. And again, we're trying to show that it is going to be capital F of x. Now, because we assume at the very beginning that yp is a solution to this non-homogeneous case, right? This will give us capital F of x. So yp double prime plus byp prime plus cy sub p is capital F of x. So this is going to be capital F of x. And what can I do here? Well, it's not quite the same as this because there's a lowercase c in front, but they all contain this factor of lowercase c. So I can factor that out in front. And you get a y sub h, b y sub h, c y sub h. It's going to be a question mark, but what is this? Well, that's a solution for this homogeneous case, so it will give us a 0, right? And c times 0 is just 0, and that is indeed going to give us the capital F of x. So this is the reason why, if you start with something that's non-homogeneous, you should always consider the homogeneous case, because the solution to the homogeneous case, you can add it on to the non-homogeneous solution, and that will be another solution. Okay, so this is the reason why we start out with a homogeneous case, study all the cases and what type of solution we get from the homogeneous case, and then we switch over to the non-homogeneous case, study all the cases for the particular solution, and then we combine the two together to give us that general solution. Okay, so let me just kind of give you a quick review on 4.2, 4.3, quick review on 4.3, 4.4, and 4.5, and then we'll do an example that will just kind of tie everything together. Maybe this one. Okay. All right, so 4.2 and 4.3, this is on the homogeneous case, a y double prime plus b y prime plus c y is equal to 0. And it turns out this is the condition that will give us a solution are of the form e to the rt, e to the rx, right? Because I decided on x being my independent variable, where r is a 0, or you can say the root of the characteristic equation, which is going to be a r square plus br plus c is equal to 0. Okay, so this is just something that you actually notice that if you differentiate this once, there's an r in front. If you differentiate it twice, you get an r squared in front. Okay, and because of that property of this exponential function, it will be a solution for this guy as long as r is a 0 of this characteristic equation. All right, so let's do an example. So we have y double prime minus y prime minus 6y is equal to 0. And so my characteristic equation is going to be r squared coming from that y double prime. A is 1, so I'm not going to write that 1 in front, but y prime will translate to r minus 6, and y would translate to nothing. It's just a 1, so it's just minus 6. Okay, so what would be all the zeros of this guy? It's r minus 3, r plus 2. So you actually get 2 zeros. So your first solution would be e to the 3x, and your second solution will be e to negative 2x. All right, so if I plug this into this original guy, I'll get a 0. If I plug this into the original guy, I'll also get a 0. So let's check. So e to 3x, if I differentiate it twice, b to the e to 3x, I'm going to differentiate it once, and minus plus c e to 3x, and it should be giving me a 0. My a is a 1, my b is negative 1, and my c is negative 6. Okay, so if I differentiate this twice, I am going to get a 1 and a 9 in front. Minus 1, because my capital B is 1. If I differentiate this once, I get a 3 in front. And you have a minus 6, but you're not differentiating, so it's just going to be e to 3x. And if you look at that, that is a 9e to 3x minus 3e to the 3x minus 6e to the 3x. So that's going to be a 0. Okay? So this is indeed a solution, and you can check that if I plug this in, this is also a solution. Now, if this is going to give you a 0, and I plug this in, it's going to give you a 0, then it doesn't really matter how many of these guys I plug in. 0 plus 0 plus 0 is still just a 0. And so you can write the general solution for this guy as any multiple of this e to 3x plus any multiple of this e to negative 2x. And this would be the solution for this homogeneous case. Right, if I plug it in, this will give you a 0. This will also give you a 0. And so it doesn't really matter what constant is in front. It's just going to be all zeros. Okay. All right, so that's 4.2 and 4.3. And then we come to 4.2, 4.3. We come to 4.4 and 4.5, which is the non-homogeneous case. So if you have this differential equation where the right side is not 0, it's non-zero, some sort of a capital F of x, you start thinking to yourself, what should y be that will give me this capital F, right? Knowing that capital A, capital B, and capital C's are all constant. So for example, you have y double prime minus y prime minus 6y is equal to x squared e to the 2x. Okay, so the rule is we're going to fall back on the 3 types of functions we know very well. If capital F of x is a polynomial of, let's say, degree n, then y, the solution, should be a polynomial of degree n. So why is that? Well, if you have a polynomial of degree n and you differentiate it once, differentiate it twice, they will all be polynomial. And here you're adding polynomial with polynomial, so you'll end up with a polynomial. And so if your capital F is a polynomial, then it's a wise guess to think that y should be a polynomial of degree n. Okay. So what's another type of function that we know very well? Well, exponential. So if f of x is some sort of an exponential function, then y, the solution, should be an exponential function. So we know this function pretty well. If you take y, which is an exponential function, you differentiate it once or twice, they're all a differential function, and so when you add them together, you should get a differential function, an exponential function. So if you start with an exponential function and you add them together, you will get an exponential function. Another type of function that we know very well would be sine or cosine. Right, so if you differentiate a sine or cosine, you will get back either a sine or cosine. So if you end up with a sine or cosine on the right side, you probably started with a sine or a cosine. And that's it. This is just the basic rule of what is a good guess for what y should be. Okay, so how do I solve this particular solution given that on the right side you have the product of the two? It's a product of an exponential and a polynomial. Okay, so what should be my particular solution? Well, it should be the general form of this guy. So if you end up with a polynomial of degree 2 multiplied by an exponential with the coefficient 2 on top, then you should probably start off with the general form of that, so e to the 2x, and then here's a polynomial of degree 2, so maybe a x squared plus bx plus c. Okay. All right, and then there's another rule. Because there is a common term between this particular solution and the homogeneous solution, this will give rise to a problem when we start to plug this in. The homogeneous part will just become 0, so it won't really contribute to anything on the right side. And the trick to kind of solve this is to start multiplying by an x, right? So if you recall, actually I'm wrong. Okay, so the two zeros are 3 and negative 2, whereas this is a positive 2, so we're okay. All right, if that was a negative 2, I would have to multiply by x, but because that's a positive 2, which is different than the homogeneous solution, we're okay. This and none of this will give us a 0, so all of these will contribute somehow to that capital F of x on the right side. Okay. All right, well, that's my solution. I got to figure out what should be my a, b, and c, so that I will get an x squared e to the 2x on the right side. Okay, so before we plug it in, we have to figure out what y prime is for this guy. So if I differentiate it once, I will get 2ax plus b e to the 2x. And now I'm going to keep that ax squared plus bx plus c, and I'm going to differentiate that second part, the second factor, so that'll give me a 2e to 2x. You're going to differentiate it a second time. So again, product rule for this guy, product rule for this guy. So if I differentiate this first product, I will get a 2a e to the 2x plus 2ax plus b, and now there's going to be a 2e to the 2x plus, and now the product rule for this one. that's going to be 2ax plus b, keeping the second factor, so it'll be 2e to the 2x. Now I'm going to keep the first, and differentiate the second factor, and that's going to be a 4e to the 2x. Okay, and so we want to figure out what should lowercase a be, what should lowercase b be, what should lowercase c be, so that when I combine all these together, plug it in here, I will get this x squared e to the 2x. Okay. Okay. All right, so I'm going to clean this up, everything up. You have a y double prime minus y prime minus 6y. So that's y double prime, which is going to be 2a e to the 2x plus 2ax plus b 2e to the 2x plus 2ax plus b 2e to the 2x plus ax squared plus bx plus c 4e to the 2x. Okay, and then you have a minus y prime, so I'm going to minus everything in the y prime, so that's going to be a minus 2ax plus b e to the 2x minus ax squared plus bx plus c 2e to the 2x. And you have a minus 6x, so that's going to be a minus 6 minus 6y, so the y is just going to be this. Okay. All right, so here's the hard part. We have to kind of gather everything and look at the coefficient of that e to the 2x. There's going to be three terms. There's going to be that x squared e to the 2x, and then you have the x e to the 2x, and then you have that e to the 2x. So we're going to look at that x squared e to the 2x term first, collect all the terms, and look at that coefficient. All right, that is not an x squared e to the 2x, and you don't have an x squared here. There's no x squared, and the first x squared e to the 2x is right here, and that's going to be a 4 times a. So it's going to be 4a, all right? 4 times a. There's no x squared here. There is an x squared here, and you get that by taking this ax squared times 2e to the 2x. And so the coefficient of that will be 2 times a, but it would be a negative 2a. And we're going to look at the next one, which is going to be this guy. And that's a negative 6a x squared. So it's going to be a minus 6a. Okay. All right. Hopefully I didn't make any mistake. Let's keep on going. So we're going to look at that x e to the 2x. And so the first x term is going to be right here. Okay, and so that's going to be 4a. All right, 4a is the coefficient of x e to the 2x. There's another x right here, and that's also going to be 4a. And there's an x here, which is going to be 4b. And there's an x here, which is going to be minus 2a. Minus 2a, okay. And there's an x here that's going to be a minus 2b. And then the last guy, which is an x e to 2x, which is a minus 6b. Okay, so that's the coefficient of x e to the 2x. The very last one will be the coefficient of e to 2 to the x. So here's the first one, e to the power 2x, and it's 2a. And the next coefficient for e to the 2x will be 2b. And this will be another 2b. And then you have 4c. Okay, so that's 4c e to the 2x, and then you have here the coefficient of 2x being a minus, just a minus b. And e to the 2x here, you have a 2 multiplied with minus c, so minus 2c. And the very last e to the 2x would be minus 6c. Okay, now this is supposed to be all equal to the right side, and so if you look at the right side, you should just have the x squared term. There's no x e to the 2x, there's no e to the 2x. So what's that going to tell me is that this should be equal to 1x squared e to the 2x. This guy should be just 0x e to the 2x, because there's no x e to the 2x term, and there's no e to the 2x term, so it should also be 0. So that's going to give us a system of equations that's going to tell us that minus 2a should be 1, right? Oh, minus 8, so minus 4a. Nope, that's a positive 2. Yeah, I'm right. Sorry, I can't add. Okay, so a is a negative 1/4. How about this one? This is going to give us 8a, which I already know is negative 1/4. And all the b's, if I add up all the b's, 4b minus 4b is not 0, and then you have a minus 6b. And that's 0. Okay, I know a is negative 1/4, so negative 1/4 times 8 is negative 2. So then I know that negative 6b is a positive 2, so b is a negative 1/3. And the very last one, 2a plus 4b, 4b minus b, so that's a 3b. 2a plus 3b, and you look at all the c's, that's going to be a minus 4c. That's also a 0. And I know a is negative 1/4, so this is going to be a negative 1/2. B is negative 1/3, so that's just a minus 1. So negative 4c is going to be a positive 3/2. And so c is going to be a negative 3/8. Okay, so that's my A, here's my B, here's my C, and this will give us the final solution. The particular will be negative 1/4 x squared minus 1/3 x minus 3/8 e to the 2x. This, if you plug it into this differential equation, you will get exactly x squared e to the 2x. Okay, but remember, we also have the homogeneous solution, which we can add on to the particular solution, because this homogeneous solution would just end up giving us a 0 if we plug it into this differential equation. And so the very final solution will be the sum of the particular plus the homogeneous solution, and it could be any coefficient in front, and this is for any C1, C2, this is the general solution. Okay. So if you give me a C1, C2, I can plug it in to this differential equation. It would satisfy this guy. So this part is particular because it will give us this x squared e to the 2x, and this part is homogeneous, so it's just going to become a 0 if I plug it in. Okay. Now, if I had started with some sort of a initial value for that solution, let's say y0 is a 5, y prime of 0 is a 1, then given this general solution, I can figure out what should C1, C2 be. So I know that y will be a 5 if I set x to be 0. Right? If I set x to be 0, I'm going to get a C1. I'm going to plus C2. If I set x to be 0, I'm going to get a what? A negative 3/8. Right? 0, 0, and then negative 3/8. And that's going to give me 37/8 as the sum of C1, C2. That's not enough to solve what C1, C2 should be, but now at least I know that if I add them together, it should give me this number. I would have to differentiate this once, and then set x to be 0, and then my y prime should be a 1, and that will give me a second equation for this in terms of C1, C2, and that'll allow me to solve for the exact value of C1, C2 that would satisfy these initial value. Okay. All right, so this is just a quick summary of what chapter 4 is all about. It does get a little bit more complicated, but I'm gonna do one more video with another solution, another example, just to hopefully clear things up for you guys. But once we get into Laplace transform, you can solve this easily with a Laplace transform. Okay, so that's it for chapter 4. Let me do one more video on chapter 4, and then we're gonna move on to chapter 7. Okay, I'll see you guys in the next video.